Okay, we're on.
Hello. Welcome to the April meeting of the Baton Rouge Astronomical Society. Our speaker this evening is going to be talking about variable stars. He's a member of the AAVSO, the American Association of Variable Star Observers, as a few others of us are too. So I want to go on and introduce you to Eric and let him talk to you about it. Eric?
Thank you. Hey everyone, I appreciate the invitation to be here. I'm really excited to be around some fellow astronomy enthusiasts. As a very brief background to me, I spent most of my life in Texas, came here to Baton Rouge about a year ago to join the physics and astronomy department as a PhD student. So that's what I'm working on at the moment. But today specifically, I'm here as a volunteer ambassador for the AAVSO, the American Association of Variable Star Observers, as many of you know. So I just want to talk to you a little bit about how you can participate in scientific discovery with variable stars and the AAVSO. Not quite. Sorry about that. I don't know why.
Well, you can't blame the equipment failure on me this time.
There we go. Okay, so a brief introduction to the organization. The American Association of Variable Star Observers connects amateur and professional astronomers through variable star research. It was founded in 1911 to coordinate variable star observations for Harvard College Observatory, and today is the world's largest association of variable star observers with participants in over 100 countries and an archive of more than 34 million observations, spectroscopic, photometric, and all kinds of things hosted there. So the AAVSO's mission is to enable anyone, anywhere, to participate in scientific discovery through variable star astronomy. So what are variable stars? Variable stars are stars that change in brightness over time. It can happen for numerous reasons, but they're divided into two primary classes. That is extrinsic variability, which can be thought of as changes in brightness due to external features, and intrinsic variability, which can be thought of as changes in brightness due to internal changes in the star. So one example of, yes, an extrinsic variable star, or system, I suppose, is eclipsing binary star systems. So these are star systems in which that are bound by gravity into a mutual orbit, and as one passes in front of the other with respect to observers on Earth, we see a dip in the amount of light that we receive. So this is a sort of cartoon example of what we call a light curve, which is just a plot of the brightness of a star over time. So a good example of an intrinsic variable star is a pulsating variable star. These are stars in which nuclear burning works against the force of gravity, causes the star to expand and then shrink on a periodic in a periodic manner, and that again changes the amount of light we receive from the star, leading to a light curve that looks somewhat similar to the one we just saw for the eclipsing binaries. So, what is the motivation to observe variable stars? They're important tools to increase our understanding of the universe. So, for example, one type of variable star, specifically a pulsating variable, is called the Cepheid variables. These are the first rung on what is known as the cosmic distance ladder. Since we can't just lay out a tape measure between astronomical objects, astronomers have had to get really clever. One such clever astronomer was Henrietta Swan-Leavitt, who in 1908 discovered the period luminosity relationship of Cepheid variables. That is the period of pulsation, the brightness, and the luminosity, which makes them useful as what's known as standard candles, objects with known luminosity which can be used to gauge astronomical distances. So, in fact, Edwin Hubble, of Hubble Space Telescope fame, although he predated it, obviously, first used Cepheid variables to identify that there were galaxies vast distances away from our own Milky Way. At the time, there was a bit of a debate whether the entire universe was sort of contained within what we know as the Milky Way, and things that we saw as, that we know now are galaxies, were just particularly bright objects within the Milky Way, or whether the universe was made up of so-called island universes, which we now refer to as galaxies, His observations of Cepheid variables in the Andromeda Galaxy, our nearest neighboring galaxy, were important, in fact, essential to settling that debate and helping us understand that the Milky Way is just one of many, many galaxies in the universe, separated by vast distances. Another motivation for observing variable stars is that they can tell us about the past and future of stars in our universe. So, for example, the Sun will become a Myra-type pulsating variable in about 5 billion years after it exhausts the hydrogen in its core through nuclear burning. Here we have a Myra variable observed in infrared, and you can see as it pulsates, it grows and shrinks. We have a light curve here, which shows the variation in the intensity of the light we receive from it over time. As stars expand and contract by large percentages, like 40% or something here, and change temperatures, the light we receive from them can vary by up to 10 magnitudes, which is the difference between the brightest star in the sky and stars that are invisible to the naked eye, even in the best conditions on Earth. So this is Chi Cygni. It's got about a 400-day period of pulsation. This light curve was over, obviously, several years. So another motivation for observing variable stars is that it's currently the best method for us to identify planets outside of our own solar system, that is, exoplanets, planets that orbit other stars in the universe. So, like an eclipsing binary system, when a planet passes in front of its host star with respect to observers here on Earth, again we see a change in the brightness from that star. Here again we've got a little cartoon light curve that you can see. There are variations in brightness as the planets pass in front of their host stars. Like I said, this is currently the best way of identifying exoplanets. Something like 80% of the exoplanets now identified have been identified through this transit method. That's around 4,000 exoplanets at the moment. The NASA Exoplanet Archive just keeps growing, and so it's sort of hard to keep track of that number, but 4,000 is a good neighborhood estimate. So we've talked a little bit about the motivations behind observing variable stars. It's important to know where you, as individual astronomers, can come in. So there are over 1 million known and cataloged variable stars, and more are discovered all the time. You can help to describe and categorize these new discoveries. Some variable stars vary over extremely long periods of time, and so we need similarly long periods of observation to describe their variability on these long time scales. You can help by monitoring these stars, the ones with particularly long periods of variation. Also, variable stars discovered by large professional surveys, like the Transiting Exoplanet Survey Satellite TESS, require follow-up observations on every variable that they identify to confirm or refute the presence of exoplanets and to describe the properties of those exoplanets. And again, you as astronomers can help to make those follow-up observations. So, as just a couple of examples here, I've got one of the oldest cataloged variables and one of the more recent cataloged variables. So, at the top right, that's the Crab Nebula. That is the remnants of a supernova that Chinese astronomers noticed about 1,000 years ago. They called it a guest star because it sort of lit up out of nowhere, stuck around for months, and then faded back to being invisible to the naked eye. And ever since, this nebula around the pulsar, which now remains as the remnant of the supernova, expands. And in fact, you can look at pictures of the Crab Nebula going back, particularly since the Hubble launch, and actually see the expansion of that nebula, which is really, really cool to see. So one of the more recent variable stars of interest is TRAPPIST-1, which is variable extrinsically. That is, the star itself doesn't have much variation inside of it, but it's got a system of 7 exoplanets that eclipse the star from our perspective here on Earth. And so as these planets pass in front of this star, we can categorize the changes in brightness, and we've described, like I said, these 7 planets that orbit it. This is TRAPPIST-1. That is, it's the first exoplanet host star observed by the TRAPPIST telescope in Chile. So, since the beginning of observations to now, there's new variables discovered all the time. Is sort of the point. So, no telescope, not a big problem. There are hundreds of variables that you can observe and make useful contributions to science with visual observations, as in the unaided eye, or with a simple pair of $30 to $100 binoculars, or as many people here probably have telescopes, you can get even deeper and make useful observations with those. But even if you don't have a telescope, it's important that you contribute your data to AAVSO or other organizations. So very few of the highly advanced all-sky surveys, like the Transiting Exoplanet Survey Satellite that I mentioned earlier, actually penetrate and observe stars brighter than 8th magnitude, which is about the brightness of Neptune. So if you observe significant variation in a star that bright, you should definitely share that with the AAVSO and the world, because there's a good chance that only you and perhaps a handful of other observers are tracking that star visually. And so again, you can make material contributions to science with that. So you may wonder, if I've convinced you to submit some of your own observations, what should you observe to contribute materially to science? So AAVSO encourages observers to choose targets based on their interests and equipment. So that's obviously the first consideration. But it's important to know that there are ongoing campaigns for visual observations of variable stars that astronomers request through the AAVSO. They have a notices board where you can see ongoing campaigns of, again, things with long-term variability or special notices for particularly bright or rare events like novae or newly discovered variables that we need to build a database of information for as fast as possible. So here we have a light curve generated. You can't quite see it. I just made this on the AAVSO website of CH Cygni. I chose this one in particular because since 2020, there's been an ongoing call for visual observations of this system. As you can see on this plot that goes back to about 2010, it shows really non-periodic variations, which have been hard to categorize. So in particular, systems like this often get requests for observation from quote-unquote amateur astronomers because they're simply too strange to sort of be done with. We need to continuously observe these sources to accurately describe them. This one, like I said, has had an ongoing call for visual observation since 2020, which persists right now. So your observations could be really important and, like I said, contribute materially to scientific discovery. So some objects, in particular recurrent novae or R corona borealis variables, that's R core bor for short, undergo really rare but extremely dramatic changes in brightness on the scale of a few years. So, for example, again, you can't quite see it. This is a light curve I created again with the AAVSO website of RY Sagittarii, which is an R core bor star. As you can see, most of the time it has sort of subtle variations between 6th and 7th magnitude, which is bright enough to see with the unaided eye in decent conditions. But every few years undergoes these really dramatic dips in brightness to as dim as 14th magnitude, which is not visible to the naked eye, even in the clearest skies on Earth. But again, that's where your binoculars and telescopes come in. So this star, RY Sagittarii, is in one of these dramatic dimming cycles. And therefore, again, there is a call for observations out for this system in particular. So often, amateur astronomers are the first ones to notice these drastic changes in novae or R core bor stars. And those observations, when submitted to the AAVSO, can help astronomers to focus the most precise and sensitive equipment we have at these systems for detailed follow-ups. So perhaps I haven't convinced you with these few examples that I've shown, but you should know that the AAVSO has opportunities for every interest, every level of experience, and your available instrumentation or lack thereof. You can attend free how-to webinars, which are in English certainly, but now increasingly in Spanish as well, to improve your astronomy skills. That's courses that range from visual observations, telescope observations, data reduction, image processing. If you're just interested in light curves, you can play around with that tool like I do on a weekly basis. You could also become a volunteer ambassador and engage in education and outreach with the perk of free AAVSO membership. That's nice. So the AAVSO has observing sections for pretty much any interest. So you can find people who share your interest in solar astronomy, in eclipsing binaries, young stellar objects, exoplanets. There's an observing section for all of them. And I even, one of my fellow ambassadors is into the astronomy side, but really heavily into graphic design, and contributes her skills by making new logos for these observing sections, like the solar one, I think is the most recent. And I think it's really cool. But so there's all kinds of ways you can participate in the AAVSO. So though many of these talks and tutorials and events, like the ones I mentioned, are free, there are certain additional benefits to paid membership with the AAVSO. You get access to the mentorship program, where you can get assistance individualized to your experience level and interests and instrumentation. That is from a quote, somewhere between professional and amateur astronomer, can help you set up your own observing program. You get remote access to a global network of research-grade telescopes through AAVSO.net. You get discounts on continuing education courses, like the AAVSO Choice courses, named for particularly avid AAVSO member, and access to the Journal of AAVSO, where many of the findings enabled by amateur astronomers are published. So, thank you for your time. These are only a few ways that you can participate in variable star astronomy with the AAVSO. I do encourage you to go to www.aavso.org to check out any of the things I discussed, in particular the calls for observation, because there are always new ones coming online, and there is a lack of citizen scientists to make the observations needed to describe these variable stars. So I'm happy to answer any questions you have now about the AAVSO, about variable star astronomy, astronomy in general, or my research. Thank you very much for the invitation. I'm very happy to be here.
I do have one question. What is the data spread on using a CFIT for a standard candle? Is it like plus or minus 10% or closer?
Are you asking what
the percent error? Because obviously there's a randomized error in using a CFIT as a distance ladder.
Mm-hmm.
But what is about the percent error? If you determine Andromeda is like 2 million light years away or whatever, what is the plus or minus usually on that?
Well, so that's really constrained by how well we can describe the period luminosity relationship of Cepheids,
Right.
which, lucky us, is like a really tight relationship.
Okay.
And so I think there we've gotten to the point where we're limited by just simply integrated exposure time. So the relationship is really, really tight,
Okay.
and we understand that to be, at least from our observations, true to the universe. And so it's really about, like I said, integrated exposure time. So if you're looking at Cepheids in the Andromeda galaxy, you have pretty good error estimates on the distance. One thing I did forget to mention, and I'm glad you reminded me, is that you use these as the first rung on the distance ladder, and then say, if you observe Cepheids in the Andromeda galaxy, and you observe a brighter event, like a supernova, you can accurately describe the brightness of that supernova, look for supernova out further to more distant galaxies, and that's how you build up your distance ladder, which I sort of neglected to mention. But the uncertainties, I believe, on the distance to Andromeda are much less than 10%.
Okay.
Yes.
So walk us through the basics of how do you measure the brightness of a star through the telescope? You got obviously some sort of sensor. Do you calibrate it against a known bright star? Or?
Yeah. So the basic setup, whether you're doing visual observations, aided observations with a binocular, or observations with a camera, a detector, The basic recipe is still to compare a source that you believe to be variable with one that you know to be non-variable. And so you can do that with the eye by sort of making a measurement of
You can, I can't.
by making a measurement of how bright it appears to be in reference to, as it's referred to, a reference star. When you're doing photometry with like a CCD, a charge coupled detector device, it's a lot more quantitative, where you can literally say the flux from this reference star and then compare it to the variations you see. But you can even do it without the camera.
Visually, like what I was doing at home is where John had. Remember? That's
Do
about
you
what
think there's
Max.
still room for visual observations and?
I can't remember what it is like. One measure next.
Absolutely, yeah. In fact, there are so many variable stars to describe, and so many of them. So there's two ways I want to answer this. One, there's just a glut of stars to observe, and not enough observers. Time on professional telescopes is limited. Even just to tell, big observatories where they ought to point things, it's important for citizen scientists to make visual observations of things that are bright enough, obviously, to see from clear skies. On the other hand, not the other hand, from a second perspective, there are stars that are too bright for, like I said, the advanced all sky surveys that we have. Really sensitive telescopes just simply can't observe things brighter than about 8th magnitude, like the brightness of Neptune. And so even if you don't have the setup or money to invest in a telescope and a detector, your visual observations of those, which are good because they're bright, help to describe the long-term variability of those systems.
So they're just, the cameras are too good.
Too sensitive in some cases, yeah. And also, a lot of the sort of refrain for astronomy has been like deeper and dimmer. Let's penetrate to farther reaches of the universe. Let's look at the objects that aren't obvious in the night sky. But no one ever finished cataloging the things that we can see from the ground. So there's still a lot of opportunity for that.
So for the visual folks,
Indeed.
get started in this, is there like a practice set to sort of acclimate?
Absolutely, yeah. So AAVSO.org, they have a tutorial for your first unaided visual observations. They've got tutorials for binocular aided visual observations that have targets, whether you're in the northern or southern hemisphere, that are easy to observe and show interesting amounts of variation, often Myra-type variables, which have significant variation over time, are fun for amateur astronomers because you can really see the difference even over hours sometimes.
And oddly enough, there's also, I've noticed this with the Sky telescope, and every month when Algol was up, they'll always print, a basic star chart. They started including brightness for comparative stars in that little chart. So there is,
Absolutely.
every month that you get Sky telescope, there's practice. And that's part of that 10 easy stars to intro.
I do want to mention, I don't know if they still have it or not. Years ago when I joined them, bought the manual on it, they have pictures of sections and they go 5 times in further to expand it out. And they have comparison stars around it, telling you to the 10th the magnitude. So when you're observing one, you use these charts and then zoom all the way in from outer ones into it there. And within your eyepiece, you'll have comparison ones. So you can look at it, says, oh, this one is 6.3, this is 6.5, and when I look at, yeah, that looks like a middle between them, so it's got to be 6.4.
And they
didn't have those charts and stuff, you can do that with.
Like in the past month or two. I mean, like you can go through, you can set the field of view that you want and the magnitude. They give you like a contour. You can turn it upside down, you can invert it left and right.
I think there's several online resources to create your own finder's charts. Thanks for mentioning that you don't have to sort of intrinsically know the brightness of a reference star, right? That information is all over.
Yeah, I mean, Sky Safari is always at the ready for me. I open it up and I look up for naked eye stuff in the eyepiece. So I've got for the double star program, you know what brightness the double star is.
The AL wants the AAVSO charts. Like, they're
Yep. Any other questions? Okay, well, thanks very much, Ed.
Thanks so much for the opportunity.
Your main focus, you're getting your doctorate, your PhD there, what's your main?
So variable stars of a kind, but not optical variability. So my research focus right now is on what are known as X-ray binaries. So binary systems of a compact object that is a neutron star or a black hole and a normal stellar companion that emit X-rays as the black hole or neutron star accretes material from the donor. So they light up really bright in outburst on ranges of years or decades, and then have relatively long periods of quiescence. This actually is a nice artist representation of Cygnus X1, which is the first extrasolar X-ray source, and also a high mass X-ray binary.
Do you do any stuff or studies or whatever with Rob Hines out there? I know he's like a accretion disk.
He is my research advisor.
Is he?
He is, yes. Thanks.
That's John, if you want to give us the outro, we'll kill the YouTube.
For what?
Just say goodnight, Gracie.
Okay. All right, then, we ended the live stream?
Yeah, on your cue.
Okay, then we got a couple of things here to go.